Okay, so what is a narrow escape problem? This is really a question in statistical physics or really probability, which is you have a domain, omega, you have a particle which starts at position y, which is doing Brownian motion. So x dot, for example, this is just purely Brownian, or not necessarily purely Brownian, you can also have a drift. But let's suppose you have a Brownian, well, this is Brownian motion. We can take diffusion coefficient equals 1, it's unimportant, but let's have it d here. And we're interested in what is the mean time it takes to find a small hole. Right? So this is the question we're interested in. What is the mean first passage time? What is the mean time for a particle x of t, for x of t to exit through the small hole? Let's call it d omega a, absorption. And so the particle starts at a point, let's say x0 equals y, inside omega, right? And so you take tau, which is the first time t at x, particle xt belongs to d omega a, condition that you started at 0, at y. And so this is tau y. And then what you do is you have to take the expectation, the average of all realization. And this is really what we call the narrow escape time. Narrow escape time, in the meantime, it takes to escape from a position, from a point in the domain. And we will see pretty soon that it doesn't actually depend on y. For y far enough from the boundary, it's actually independent on y. Okay, so the question, how do you calculate this time? So basically you have a particle that moves along Brownian motion in the domain. You're interested in what is the time it takes to hit here, and you repeat. This is important in particles, in channels, because this is the arrival time of an ion to a channel. This is the generic question of the arrival of an ion, or particle, or molecule, to a target. And this is a purely geometrical problem. How it depends on the shape of the domain. Now we have to, of course, make some assumption about the geometry. Because what can happen? So this is a question that, can you think in dimension 2? This is the surface trafficking of a receptor on the surface of a membrane. If you think about neurons, or probably during cell-cell adhesion for immune system to recognize one, you need molecules to go and to find small region and to be able to do this recognition. So probably this is also an important process here to define timing. And in dimension 3, you can think about how long it takes for calcium or any ions to find a molecule of interest. So of course, if you have a domain like this, if you have a small hole here, now if you start here or you start there, if the dimension here is of the same order as this, then it's not going to be the same. Because obviously you have two small holes, a small hole here and a small hole there. So we are going to work for simplicity. In fact, I'm going to ignore this. For the calculation, we can have this, but this has to be much bigger than this. so that you don't have here at a first time, which is a time to escape through here. And but this is also important. If you think about when two cells start to divide, usually you have molecules or proteins in one cell, and when you do the separation, this small hole will prevent some of the molecule, if you have the daughter cells, to go through from the mother cell to the daughter cells. And so diffusion in this double shape like this is also important. But so in general, we are going to look for calculation in the domain with no such property, so that there is no the assumption that we're going to make on the domain there are no narrow passages with the same order. Order means the length here of the passages of the same length compared to the small hole d omega, which means that they all have, if you have this, then the distance here has to be much bigger than this, right? So if it's happened, the distance here for the passages, not define it exactly, but has to be much bigger than the size d omega a. Okay, so now this becomes a question in geometry and probability. So we need to calculate this mean first passage time. So how do we calculate this? So this is what we have discussed at the beginning of the class, if you remember. So what is the mean first passage time equation? The mean first passage time equation is d, when you have a stochastic process like this, do you remember? So it's d Laplacian u plus, what is b? What is the term of order 1? Here, 0, there is no, so plus 0 equals minus 1. Then we have, what is the condition on the small hole? When the particle reaches a small hole, it is absorbed. So this is u equals 0 on the small hole. And what happens on the parts of the boundary where the particle is not absorbed? It has to be reflected. So what is the condition of reflection? This is Neumann boundary condition, which is u dn equals 0. And we're trying to find the solution, u. So the goal here is to calculate this. So we are interested in calculating u epsilon of x. And epsilon here, this is the ratio of the total absorbing boundary divided by the total boundary. So this occupies, if you look at this divided by the total boundary, this has to be very small. And so what do you expect when epsilon is small for this time? The time. What happened for the mean first passage time? Let me rest. What happened for the mean first passage time as epsilon goes to 0? If you do an experiment, so you have your particle, and the time gets the hole is smaller and smaller and smaller in your simulation. The time will get bigger, bigger, and bigger. So when epsilon goes to 0, the time should go to infinity. Now the question is how it goes to infinity. It becomes a singular perturbation problem. When epsilon goes to 0, the time goes to infinity. So we need to find out what is how it goes to infinity. Does it go to infinity like in mean first passage time when you have a potential well? When we have a potential well, how it goes to infinity? Like exponential of constant divided by epsilon. This is what we have seen last week. So is it the same here? This is the question. Okay, so now we know that it goes, as epsilon goes to 0, goes to infinity, but we don't care that it goes to infinity. Here I would like to know how it goes to infinity with epsilon. So, how u epsilon of x goes to infinity as epsilon goes to 0. So this is the question we're interested in. All right? So let's spend 10 minutes to start the process of solving a question in probability using partial differential equation by doing asymptotics on u to derive the behavior. So what do you expect? What do you expect about u epsilon? First of all, does it depend where you started?
No.
That's right. Except where?
You're very close.
That's right. So if you start here, of course, or if you start very close, the time will go to 0 because so the time here, if you start at the boundary, the time is almost 0. You just escape. So here you expect that it goes very quickly in the boundary layer from 0 to something that goes to infinity. Okay, so we expect to find a solution of the form u epsilon of x equals c epsilon that will go to infinity as epsilon goes to 0. This is outside the boundary layer, and in the boundary layer it's going to be a function, whatever, phi epsilon of x, that will go very quickly from 0 to something that is very high. But far away, so that is outside the boundary layer here, the solution is going to be constant. This is a constant. Okay, so this is what we're interested in, finding this constant. And if you're interested, you can also derive an equation for the boundary layer. Okay, so now how do we solve this? To solve this, we need to, there are two methods presented in the literature. So remark, there are two methods. One is called match asymptotics. And the second is called the Green's function method. So match asymptotics consists in finding a solution here, finding a solution outside, such that they do match. That is, they have some continuity of the function and the first derivative. And then you can get information. You can get a lot of information using this method about the expansion of u as a function of epsilon, where you see at first order is independent of epsilon, but then when you calculate the second order term in epsilon, you see the dependency in the position. And so this is a method mostly developed by the group of Michael Ward in University of British Columbia, which again, I'm not going to discuss much, but you can go to his website. He has a lot of publication on this. And we're going to develop our method that we developed This is, for example, you can find this in my book with shoes. This is in the book of stochastic narrow escape. This is a Springer. This is 2015. Right, so there are two methods, and I will discuss the second one. Okay, so have you ever heard about Green's function? Yeah, shall I make a small summary to have everybody on the same page? Okay. Okay. All right. So, what are Green's function? So basically, I don't know if you remember your electrostatic classes. So this was the introduction. Now we go to part 1 or part 2. This is Green's function. So basically, if you are in R2 or in Rn, what is the solution of the equation? Minus Laplacian Green's function equals delta Dirac at a point P. So suppose you're in dimension 2 or 3. For example, if you're in dimension 3, for n equals 3, you can impose that the Green's function is positive and g of x, so this is Laplacian with respect to x, goes to 0 when x goes to infinity. So you remember, sorry, in electrostatic, you have a charge, you put a charge somewhere and you calculate the potential. This is called, so the solution of this is called the Green's function of the Laplacian. So you remember what you give, what you obtain. So in principle, it's not very hard. By symmetry around the point P, the field is independent of any variable except the distance. So the Green's function, the Laplacian in dimension 2, this can be written dg dr squared plus n minus 1 divided by r dg dr equals 0 outside the singularity for r not equal to 0. And at 0, g of r goes to infinity when r goes to 0. Now you can go in here and just integrate. If you integrate twice, what do you get? So it's not very hard. Right, this is second derivative, n minus 1r, first derivative equals 0. So you get second derivative divided by the first derivative. Oh, sorry, I'm starting to be tired. Is n minus 1 divided by r. You integrate once, you get log of g prime equals minus 1 log of r. And then you get plus a constant. And then you get g prime equals, so r n minus 1 plus a constant. And if you integrate one more time, you get this equals, are we correct? Yeah, it's a constant. So now you have, no, it's not, it's incorrect. So this constant is here. And there is no plus because I take, it's a log. And so if you integrate one more time, you get a constant C1 divided by Rn minus 2 plus constant C2, correct? This is if n is different of 2, and if n equals 2, when you are here, if you have 1 over r, if you integrate, you get log. So in general, it's log a constant log of R plus C2. So C1 plus C2. Okay, so if in addition you impose that in dimension 3 that this goes to, this goes to 0 when R goes to infinity. So at infinity this is 0, so C2 must be equal to 0. So in dimension 2, C2 is equal to 0. Dimension 3, sorry. And how do you calculate the constant C1? So C1 is, of course, if C1 is 0, doesn't work, right? You have 0 and it cannot satisfy delta Dirac. So you can see that this goes to infinity for C1 not 0 when R goes to 0. And now you can calculate the constant C1, because if you integrate the equation, Laplacian equal delta Dirac, so you integrate over any ball of radius R, any ball of radius R. So what is the integral of delta Dirac? I know there's something. What is the integral of delta Dirac? It's equal to minus delta Dirac, if you integrate, is equal to if you have delta Dirac,
Outside.
what?
Is it inside or outside?
Yeah, I'm sorry. I took the equation here and I integrate, so we have d of x dvx. And so this is an identity equals the integral of delta Dirac at position x at point P, dvx. So if the point P is inside the ball, a delta Dirac of an integral is by definition delta Dirac. If the point is outside, delta Dirac is 0. So integration of 0 equal 0. But if the delta Dirac is inside, by definition, then if you integrate something with a density, and it is normalized to 1. So this is exactly equal to minus 1. Okay? Now, by the Gauss integral, the divergence of this is Laplacian. Laplacian is divergence of the field. So this is exactly equal to dj dn d ball of radius r. You integrate the flux. So this by definition equals to minus 1. I put d equals 1 here. So dg dn, now we have to calculate the derivative. It's equal to a constant r to minus n, and so we integrate over the ball of radius r, which is r, multiplied by, so this is ds, so this is the surface of the ball of radius n minus of the sphere, multiplied by r n minus 1. Am I correct? I hope so. So if I remove this, I remove that. No, I'm sorry. Let's do it properly. I have this, so if you differentiate g prime of r, this is minus c1 r divided by n minus 1 multiplied by n minus 2. So the constant that I want to put in here, this is minus c1 n minus 2. This and this goes, and finally minus and minus cancel, and I have c1 equals to what? 1 divided by n minus 2 multiplied by omega n minus 1, which is the volume of the unit sphere S n minus 1. So for example, in dimension 3, it's the dimension 3, it's the surface of the sphere. What is the surface of a sphere in dimension 3 of radius 1? It's 4 pi. Right? So in dimension 3, 3 minus 2 equals 1 multiplied by 4 pi. So in dimension 3, we get what? We get the Green's function. So the Green's function really depends on 2 points, P and Q. Q is the variable and P is the point where you have your singularity, equals 1 divided by 4 pi, the distance P minus Q. This is the classical result in electrostatic, no? Don't you remember, if you put a charge at a position P and you look at position Q, the charge depends only on the distance P minus Q. So this is the classical result. Agree? All right. So this shows that the Green's function has a singularity. When P goes to Q, it goes to infinity, and with 1 over R, 1 over the distance. Okay? Okay, in dimension 2, I'll leave you you do it at home. Then we'll stop for today because I'm getting tired. In dimension 2, the Green's function is minus 1 divided by 2 pi log of the distance between the point P and the point Q. And now we can do the same inside the domain. So this is in the free space. I put a particle, charged particle in the space, you look at the distribution of voltage. Now, in the bounded domain, it turns out that you can define Green's function. So Green's functions, the Green function is solution of minus Laplacian Green's function equals delta Dirac at the point P, you're inside the domain, to point P. So we have the Dirichlet Green's function, which is the Green's function. So I call G the depend on P here at point Q equals 0 on the boundary, all Q on the boundary. So this is called the Dirichlet Green's function. And so I'm not going to prove this, but the Green's function exists, it is unique. So there exists such a function. It exists and it is unique. And what is interesting is that when you go close to the point P, you have the same singularity as if you were in the infinite space. And this is important. It's going to be important for us. So the Green's function can be written as 1 divided by n minus 2 p minus q plus a function p and q which is regular, which has no singularity. So you can always write it this way. So again, we're here. This is in dimension 3. It's also true actually in all dimensions, as long as you are in Rn, in the Euclidean space. If you are on a manifold, this could be a bit more complicated. Okay. So there exists such a function, it has such behavior, that is when P goes to Q, this is regular, so you can neglect it, and this is the singular part. But there is another type of Green's function, so this is called the Dirichlet Green's function. So this is 1. This is called the Dirichlet-Green's function. And now I want to introduce, and then we'll stop, the Neumann-Green's function. The Neumann-Green's function satisfies the same equation, which is Laplacian equals delta Dirac, but except that on the boundary, we have Neumann boundary condition, which is dj dn, the derivative with respect to the normal, equals, for example, here a constant. And of course, the constant has to be very specific, because if you integrate this the same way we just did it 1 minute ago, we get minus Laplacian j equals delta Dirac, integration of delta Dirac, which is 1. And this is exactly dj dn. But since dj dn is constant, this is a constant. And so we have to integrate the constant over the entire boundary, which means that the constant multiplied by the boundary equals minus 1. So this is, the constant can only be equal to minus 1 divided by the boundary surface. And again, the Green's function exists. And now what is interesting, so this is a theorem, but I'm not going to prove anything, I'm just going to tell it to you. So the Green's function j exists and is unique up to a constant, because here, if you add a constant in here, the Laplacian of a constant is 0 and the derivative of a constant is 0. So it's up to a constant and it has the same shape. You have P and Q if P belongs inside the domain and Q is inside the domain. The Green's function is again of the form of 1 over n minus 2 P minus Q plus a regular function. But the new thing here is that when the point P, now when P is on the boundary, and this is incorrect because there is an additional singularity, and the Green's function becomes equal to 2 divided by n minus 2 for regular domain, P minus Q plus RP and Q for a domain where d omega is regular. So d omega, regular domain. So let me explain this and then we stop. Why? Why do we have this? If you have studied some physics, you will understand it immediately. If you have a dielectric, if you put a charge here, then we have exactly the solution of this equation, Laplacian equals delta Dirac at point P. And here we need to have dj dn equals 0 on half the plane. So how do you construct a solution of this equation? We just saw what happened in the entire space. We saw that the solution is equal to, I just erased it. See, if you have the entire space, what is written on the note is that the Green's function equals 1 divided by 4 pi P minus Q. This is what we did 1 second ago. Now if you add here this condition, how do you find the solution for this equation with this boundary condition? You have to add an image charge, which is you take the reflection of this let's call it p tilde. And now if you take this function and you add 1 divided by 4 divided by p tilde minus j, so you do it as an exercise, this satisfies exactly this, because we're interested in half of the space. This satisfies exactly this equation. And now if you differentiate, and look at what happened on the boundary, you see that this is 0. Now, what happened if you take, for example, the point P, and you put it on the boundary? If you put P on the boundary, P and P tilde will be the same. So what you get for Q, when you have the singularity at 0, you get twice the term here. And so you get twice, so this is twice divided by 2 pi, 1 divided by Q, when the singularity, when P now is at 0. So you see that there's, sorry, 4. So you see the factor 2, where it comes from. And this is the same on the domain. If you have a point, the singularity on the domain, on the boundary of the domain, you'll have this singularity. And this is going to be important when we are going to do the calculation, because we're going to look at what happened at the boundary, which will give us an additional singularity. Okay? I think we did a lot today. It's a lot of physics, mathematics, asymptotics, but this is the way to go. About modeling biological questions. If we have strong mathematics, we can solve non-trivial questions, not just by moving things. For example, geometry is important. We know in biology, in cellular biology, geometry is a lot. All cells have particular geometry, all targets, all proteins are usually very well positioned. And so PDEs, this is exactly what PDE's partial differential equation is giving us. It's giving us a tool to address the question of the geometry. And now we're using the Green's function to capture the geometry. So we can calculate, for example, rate constant, how rate constants depend on the geometry. Why this is important? Because if the geometry starts to change, you can see how by changing the geometry, you can regulate the rate of arrival and just you regulate the production. Or, for example, for gene expression. Okay? Next week, I'm around. We'll continue. We'll finish. I hope probably I'll finish narrow escape and diastrate, and then we'll be ready in 2 weeks from now to start application to biology and cell biology, data analysis. Okay? All right.